Hello and welcome everybody to the physics pages. Today I'm going to explain IGCSE physics paper 42 code is 0625. It is extended version of October November 2024. Let's start our exam. Question number 1, part A says rocket has initial mass of 7.4 times 10 to the power 6 kilogram. We have to calculate the initial weight of the rocket. So first of all, I would like to talk about the weight. We know that weight is the mass times gravitational acceleration or free fall acceleration. Symbolically, we can say W for the weight is equal to mass m and g the gravitational acceleration, where we know that it's mentioned that gravitational acceleration or free fall acceleration is 9.8 meter per square second. So what I will do, I will just find the weight W, or the weight is equal to mass is 7.4 times 10 to the power 6 kilogram times 9.8 meter per square second. We also know that this unit of G is Newton per kg as well. So we can just say Newton per kg. So if we multiply them, so I can get 7.4 times 9.8. It gives me 7.25 into 10 to the power 7. 7.25 into 10 to the power 7. And when we talk about the units, I told you the unit of mass is kilogram and the unit of gravity is Newton per kilogram. So weight unit will be kilogram, kilogram cancel, so it will be Newton. So I can just write in two significant figures as 7.3 times 10 to the power 7 Newton. On the other hand, part 2 says define in words the term weight. First of all, weight is a pull. We can also say force of gravity. Weight is a force of gravity on an object. We also say that weight is the force due to which Earth attracts every object toward its center. So we can also say it's a vector quantity, it's a force. So we can write in any way like this. Here is a graph given. Figure 1.1 shows a part of the speed time graph for the rocket as it leaves the ground and travel into the space. There's a rocket that is moving into the space. So the rocket that is moving into the space graph is shown. There are two parts of the graph, OA and OB. This is speed time graph. So first of all, we need to understand few important points for the speed time graph. First and foremost thing is whenever we have a speed time graph, the gradient of the speed time graph gives us acceleration. If the graph is a horizontal line, like you can say if the graph is like this straight line, then the acceleration will be 0. On the other hand, if the graph is a vertical line that we can say like this, so acceleration will be undefined. But if the graph is an inclined line, like A to B is an inclined graph, inclined. So this inclined graph will show that the acceleration is constant. So acceleration is constant from A to B. Fifth point is if graph is a curve sloping upward, like you can see here, O to A is a graph that slopes upward. This is showing that acceleration is, this is sloping up. This is sloping upward, so acceleration is increasing. So you can say this graph is showing acceleration is increasing. So I just need to remove this line, sorry for that. Acceleration is increasing, increasing. So we will say acceleration increasing. The last point and foremost, if the graph is curved sloping up with decreasing rate. What is decreasing rate? That if the graph is like this one, this is decreasing rate. So in this case, we can say that the acceleration is decreasing. So you can say acceleration is decreasing. So now moving to the question, that is first part of part B, describe the motion of the rocket from O to A. As I mentioned, O to A is the graph sloping up, graph sloping with increasing rate. So when this is happening, we say that acceleration is increasing. So you will say acceleration is increasing. On the other hand, from A to B, we can say it is inclined graph. So you can say acceleration is constant because speed is increasing with the constant rate. So acceleration is constant. Acceleration is increasing from O to A and acceleration is constant for that. Part 2, draw a tangent to the graph. You know the tangent is a line that touches the graph at one point, at point 400 second, and used to calculate the acceleration. As I mentioned in previous part, the gradient of the graph gives us the acceleration. So this is our graph. The point 400 is at this one. This is the 400 point. I can just mention it like this. This is the 400 point. At this point, we are asked to draw a tangent. So I am going to draw a straight line at this point. This is the straight line at this point. Now, this straight line we have to use to find the gradient. So for that purpose, I will need two more lines from two different points for rise and run. For example, I choose 2 points here. One point I choose for this, and the other point I am choosing this. So this will show me rise, that is delta y, and this will show me delta x. I can also choose any other 2 points to make it more simple and easy to find. Let me choose the other 2 points. I can just say that the first point is this one, which has 200 and 0, and here on the other hand 400 and 4000. So here I can just simply say that delta y is 4000 and delta x is 400 minus 200, that is 200. Acceleration is gradient of the graph, gradient of graph at time 400 seconds, that is rise over run, and rise we just found is 4000, and this one is the speed. I can just simply say meter per second, and time is 400 minus 200. I can just simply say 400 minus 200 seconds. So it will be 4,000 meter per second over 200 second. So that gives me 20 meter per square second. Rockets are used to launch a satellite into space. When satellite is released, the rocket returns to the Earth. Okay. Explain in terms of forces why a rocket reaches the terminal velocity. The terminal velocity is a velocity that is a constant velocity when net force on the object falling toward Earth becomes zero. Let's say this is the rocket, and this rocket is now falling back to the Earth. So this rocket is falling. When this rocket is falling, as it goes down due to gravitational pull, so you can say pull of Earth or gravitational pull make its speed increasing. As the speed increases, there is an upward force. So this is downward force that is pulling it out. So there is, as speed increases, upward force keep on increasing. This is upward air resistance force, the force of air resistance. So force of air resistance also increases upward. This air resistance force keep on increasing as the speed increases. So there is a moment when both of the forces, the upward force becomes equal to the downward force. As I mentioned, upward force is the drag force or air resistance, and the downward force is the force of gravity. So you can say gravitational pull. So both of these forces becomes equal. When these become equal, so you can say the net force, because these forces are balanced, become zero. So whatever the speed at that moment acquired by the rocket, that speed becomes constant because no net force is acting on it. So this constant force is called terminal speed. So we name it terminal speed. So same thing as I mentioned here, what happened is the gravitational pull increases the velocity of the rocket downwards, due to which the air resistance upward increases until it balances the gravitational force, and the net force on the rocket becomes zero. As a result, it moves with a constant velocity named as terminal velocity. Question number 2. Figure 2.1 shows a golfer about to hit a golf ball with a golf club. That you can see, this is the golf club and he is going to hit the ball. The initial momentum of the golf ball is zero, that this ball is not moving. So you can say initial momentum P is equal to 0 kilogram meter per second. We have two units of the momentum. One is kilogram meter per second, or you can also say Newton second. So you can also write it 0.0 kilogram meter per second or Newton. Part A. Define momentum. Momentum is usually product of mass and velocity. So you can just simply say momentum is product of mass and velocity. It's a vector quantity and its unit is kilogram meter per second or Newton second. Symbolically, we can say momentum P is equal to m times v. We can simply say that. Part B. The golf club is in contact with the ball for 5 times 10 to the power negative 4 seconds. It's around zero point 0.5 milliseconds. The velocity of the golf ball as it leaves the club is 41 meter per second. We are aware that initial velocity u, it was not moving, it was zero point 0.0 meter per second, but the final velocity is 41 meter per second. Now the golf ball has a mass of 0.046 kilogram. The third thing we have, the mass is 0.046 kilogram. Also we are aware that time interval is given to us, delta t is 5 into 10 to the power minus 4 second. Here we are aware about one thing, that whenever we are concerned with the impulse, impulse has two main definitions. First of all, we know that impulse is the force on an object for large force for very short interval of time. This is one definition. And another definition of impulse is it is also called change in momentum. So we can say impulse is equal to delta p, or you can say m delta v. And when you use it, we can simply say it is m times final velocity minus initial velocity is impulse. And usually we denote impulse with I. So here, first thing first, that we have mass, we have final velocity and initial velocities, and its change in momentum, its unit is kilogram meter per second. So let us solve the values. Impulse is 0.046 kilogram, final velocity is 41, initial velocity was 0, so we can simply say impulse is 0.046 kilogram times 41 minus 0, it goes to 41 meter per second. When we multiply 0.046 with 41, we get it 1.886. So impulse is 1.886. Either you can write Newton times second or kilogram meter per second. For two significant figures, I will remove this 86 because it's more than 50. So I will increase the previous number 8 by 1. So my final answer will be 1.9 kilogram meter per second, or we can simply say Newton second. Let's move to part 2. Calculate the force applied. We are going to find force applied to the ball. So for finding force to the ball, I will use the first equation of the impulse that I wrote above. I'm going to rewrite it. Impulse is equal to force into time. If I try to draw the triangle, I can just simply say that impulse is force into time. So here I need to find force, so I can rearrange it. Force is equal to impulse divided by the time interval, just substituting the values. Once we substitute the values, it would be force is equal to 1.9 kilogram meter per second over the time of 5 times 10 to the power negative 4. The answer is 3800 Newton. So I can just finalize it because it's in two significant figures. So the final answer is 3800 Newton. So this is our final answer. Question number 3. State two energy resources for which the radiation from the sun is the main source of energy. There are many sources, like you can say solar panels, also wind turbines, we also have biomass or biofuel. We can use any two of them. Solar panels convert sunlight into electricity. Wind turbines use solar energy that causes temperature difference due to which wind blows. Temperature difference to wind blows, blowing up wind. Similarly, biomass and the other can be discussed. Question number 3, part B. A wind turbine is used to generate electricity. Like I just told you, that wind turbine is converting temperature difference, uh, solar energy that causes the thermal difference of temperature, and then wind turbine works. The useful output from the turbine in 1 second is 6,000 joule. The kinetic energy of the wind hitting the turbine in 1 second is 11,000 joule. So we have output of 6,000 joule in a second, whereas input of 11,000 in a second. The velocity of the wind hitting the turbine is 6.3 meter per second. First part says show that the mass of air hitting the turbine each second is approximately 550 kilogram. We know that kinetic energy is equal to half times mass times velocity square. So from this I can just substitute the values. Kinetic energy per second, we know that is it's about hitting. So it's 11,000, half, mass is unknown, velocity is 6.3 square. I will move this 2 on the other side. So this will change into 22,000 joules is equal to mass times 6.3 square. Now I will move this 6.3 square on the other side. It will change into 22,000 divided by 6.3 square is equal to mass 554.295 kilogram. Converting into two significant figure, 554 can be rounded to 550 kilogram. That is our desired answer. Part 2, calculate the efficiency. We are aware that efficiency is output work over input work times 100. This gives us percentage efficiency. You may assume that all the kinetic energy stored in the wind is transferred to the turbine. So the energy stored in the wind is transferred to the turbine, as it was clear here in the question that useful output in 1 second is 6000 joule. Here I would like to mention output is your power, and power is always energy into time. So input energy and output energy. So I can use output energy into time, as time is 1 second. So I can neglect it, but I just want to be sure that output energy into time over input energy into time by multiplied to 100. Here I will substitute the values. I can get efficiency is, this was 6000 times 1 second over 11,000 times 1 second. As both of the fractions contains 1 second, we can also write it as 6000 over 11,000 times 100. It gives me 54.55%, and I can round it to 55%. In part C, the tidal energy. We know that tidal energy is energy created by moon's gravitational pull or earth sun's gravitational pull, and wind energy is created by the wind, are both renewable energy sources, mean they can be created again and again by without using any resources. Suggest one reason that the tidal energy is more useful energy. We are going to ignore the cost of construction and maintenance. So, first of all, tidal energy is more reliable, more predictable. I will rate it predictable because tidals or the tides are very predictable. It always have a continuous pattern, but wind, when it will start blowing, we are not very aware, very well aware about this. So this is predictable and and reliable. We also have another thing, that tidal energy is more powerful because tides have water is heavier than the air, so we can generate more power than tidal. So tides produce more power than wind. So we can write any of these two for our choice.
Physics 0625, Paper 42, Winter 2024. Question number 4. Figure 4.1 shows a pressure cooker on an electric heating element. The cooker has a tight fitting lid. Part A. The pressure cooker is half full of water. As the water is heated, some water evaporates. Before the water boils, Describe two differences between evaporation and boiling of the water in the cooker. We are aware that evaporation and boiling are both processes where a liquid turns into a gas vaporization, but they differ in how they occur and the conditions required. Evaporation is a slow process that occurs at the surface of a liquid below its boiling point, while boiling is a rapid process that occurs throughout a liquid when it reaches its boiling point. We can summarize it as: boiling happens at a specific temperature, the boiling point, whereas evaporation can occur at any temperature above the freezing point. Boiling occurs throughout the liquid. Evaporation occurs at the liquid surface. There are some other differences, like boiling is a rapid phase change, while evaporation is a slower process. Boiling requires a continuous external heat source to maintain the temperature and phase change, while evaporation can occur using the internal energy of the liquid. Bubbles are visible in boiling, whereas evaporation does not produce visible bubbles. Physics 0625, Paper 42, October-November 2024. Question number 4, Part B. As the water is heated, the pressure of the gas inside the cooker increases. Explain this increase in pressure in terms of particles. The perfect and simplified for this question could be: as we heat the water, water molecules gain kinetic energy. They start moving faster and collide with each other and with the walls of the vessel within which we keep it. This changes the momentum and exerts more force. We are aware that the force per unit area is pressure. The molecules apply more force per unit area of the wall, which enhances the pressure inside the cooker. So, we conclude that the pressure also increases because faster-moving gas particles hit the walls harder and more often.
Physics 0625, Paper 42, October-November 2024. Question number 5. On a sunny day, the temperature of a black tarmac road and the air above it both increase. Part A. Explain why the surface temperature of the tarmac increases. The black tarmac gets hotter because dark surfaces are excellent absorbers of heat, especially under sunlight. Being black, the tarmac absorbs more infrared radiation from the sun than it reflects. As a result, its internal energy increases, causing its temperature to rise. Part B. State the method of thermal energy transfer from the tarmac to the air immediately above the road. The heat from the hot tarmac transfers to the air molecules that are in direct contact with it. This process is called conduction, where heat energy moves through direct contact between particles. So, the method of energy transfer from the tarmac to the air is conduction. Part C. State the main method of thermal energy transfer from the air immediately above the road to the rest of the air. We know that when air gets heated, it becomes less dense and rises. Cooler air then moves in to replace it, creating a convection current. Therefore, the main method of heat transfer from the air above the road to the rest of the air is convection. Part D. Explain why the surface temperature of the tarmac is higher than the surrounding air temperature. Dark surfaces, like black tarmac, absorb heat much more efficiently than lighter surfaces or transparent substances like air. Air does not absorb sunlight as effectively as tarmac. Additionally, the tarmac is a poor emitter of heat, meaning it retains heat for longer. The large, thick surface of the tarmac exposed to the sun further contributes to its higher temperature compared to the surrounding air. Physics 0625, Paper 42, October-November 2024. Question 6. A student plays the violin near the doorway to a large room. Figure 6.1 shows a young teacher standing where he can hear the sound but cannot see the student. Part A1. State the wave effect that allows the young teacher to hear sounds from the violin at the position he is standing. The teacher is able to hear the violin because sound waves bend as they pass through the doorway. This bending of waves around obstacles is called diffraction. Therefore, the wave effect responsible for this is diffraction. Part A2. Calculate the frequency of sound with a wavelength of 0.75 meters. The speed of sound in air is 340 meters per second. We are given by wavelength, which is denoted by a Greek letter lambda is 0.75 m. Speed of sound, E is 340 meters per second. We are required to find the frequency, F, using the formula V equals F times lambda. Rearranging for frequency, F. We get F is equal to speed V divided by lambda. Substituting the values, F equals 340 divided by 0.75, which results to 453.33. Solving for the units meter per second divided by second gives up per second, which is known as hertz. Rounding to two significant figures. The frequency is 450 Hz. Part A3. A violin produces sounds in the frequency range 200 Hz to 3800 Hz. The width of the open doorway is 0.75 meters. Explain why the young teacher hears the frequency calculated in Part A2 clearly but finds a frequency of 3500 Hz harder to hear. The ability of sound waves to bend around obstacles, or diffraction, depends on the relationship between the wavelength and the size of the gap, in this case the width of the doorway. Waves with longer wavelengths, which correspond to lower frequencies, bend more effectively if their wavelength is similar to the size of the gap. The frequency we calculated earlier, 450 Hz, has a wavelength close to the width of the doorway, allowing it to diffract easily. In contrast, high-frequency sounds, like 3500 Hz, have much shorter wavelength. These short wavelengths do not bend well around obstacles, making them harder to hear from behind the doorway. Therefore, the teacher hears the 450 Hz sound clearly, but finds the 3500 Hz sound much harder to hear. Part B. A plane mirror is placed at point X so that the teacher can see the student. On Figure 6.1. Draw a light ray from the violin to point X and from point X to the teacher. Draw and label the mirror. Add an arrow to the ray to show how the teacher sees the student. Use a ruler and sharp pencil for this drawing. First of all, we have to draw a mirror having one silvered side while other is shiny. Now we have to draw an incident light ray from the violin to point X, which is labeled as an incident ray. Another ray from point X to the teacher is labeled as the reflected ray. A dotted line represents normal. The angle of incidence I is mentioned between the incident ray and the normal. Also the angle of reflection R, which is between the normal ray. Here we need to take care that angle of incidence I should be equal to angle reflection R. Physics 0625 Paper 42 October-November 2024. Question 6. A student plays the violin near the doorway to a large room. Figure 6.1 shows a young teacher standing where he can hear the sound but cannot see the student. Part A1. State the wave effect that allows the young teacher to hear sounds from the violin at the position he is standing. The teacher is able to hear the violin because sound waves bend as they pass through the doorway. This bending of waves around obstacles is called diffraction. Therefore, the wave effect responsible for this is diffraction. Part A2. Calculate the frequency of sound with a wavelength of 0.75 meters. The speed of sound in air is 340 meters per second. We are given by wavelength, which is denoted by a Greek letter lambda, is 0.75 m. Speed of sound, e is 340 meters per second. We are required to find the frequency, f, using the formula v equals f times lambda. Rearranging for frequency, f, we get f is equal to speed v divided by lambda. Substituting the values, f equals 340 divided by 0.75, which results to 453.33. Solving for the units meter per second divided by second gives up per second, which is known as hertz. Rounding to two significant figures. The frequency is 450 Hz. Part A3. A violin produces sounds in the frequency range 200 Hz to 3800 Hz. The width of the open doorway is 0.75 meters. Explain why the young teacher hears the frequency calculated in Part A2 clearly but finds a frequency of 3500 Hz harder to hear. The ability of sound waves to bend around obstacles, or diffraction, depends on the relationship between the wavelength and the size of the gap, in this case the width of the doorway. Waves with longer wavelengths, which correspond to lower frequencies, bend more effectively if their wavelength is similar to the size of the gap. The frequency we calculated earlier, 450 Hz, has a wavelength close to the width of the doorway, allowing it to diffract easily. In contrast, high-frequency sounds, like 3500 Hz, have much shorter wavelength. These short wavelengths do not bend well around obstacles, making them harder to hear from behind the doorway. Therefore, the teacher hears the 450 Hz sound clearly, but finds the 3500 Hz sound much harder to hear. Part B. A plane mirror is placed at point X so that the teacher can see the student. On Figure 6.1. Draw a light ray from the violin to point X and from point X to the teacher. Draw and label the mirror. Add an arrow to the ray to show how the teacher sees the student. Use a ruler and sharp pencil for this drawing. First of all, we have to draw a mirror having one silvered side while other is shiny. Now we have to draw an incident light ray from the violin to point X, which is labeled as an incident ray. Another ray from point X to the teacher is labeled as the reflected ray. A dotted line represents normal. The angle of incidence I is mentioned between the incident ray and the normal. Also the angle of reflection R, which is between the normal ray. Here we need to take care that angle of incidence I should be equal to angle reflection R. Physics 0625, Paper 42, October-November 2024. Question number 7. A washing machine has an electric motor and an electric heater. This one is an electric heater. This is an electric heater, and this one is an electric motor. The electric heater and motor you can see are connected in parallel. This is a parallel combination. Also, parallel to the power source. Figure 7.1 shows a simplified circuit diagram for the washing machine. The heater has a resistance of 25 ohms. This one is 25 ohms, and EMF of the power supply is 230 volts. Part A. State the meaning of electromotive force. First things first. Electromotive force is not a force. It's the energy. The energy provided by the battery or the power source. So, electromotive force is energy provided by the battery to a unit positive charge, or simply a unit charge when it moves through the circuit. Or, in another way, we can simply say it is the work done by the source. The source can be a battery or a power supply. Work done by any provided source in moving a unit charge around a circuit, or as I mentioned earlier, we can simply say that EMF is the energy supplied by a source per unit charge. On the other hand, we can say that it is the potential difference across the heater. It is also asked in Part B, state the potential difference across a heater. We know that heater is connected in parallel to the power source. When the heater and power source are in parallel, you can simply say, the amount of voltage source that is 230 volts is also around the terminals of the heater. So, I would prefer to write that the potential difference around the heater is 230 volts. Part C. Calculate the current in the heater. When we are asked to calculate the current, first of all, we need to remember the relation between current, EMF, and resistance known as Ohm's law. According to Ohm's law, EMF or potential difference V is equal to current I time resistor R. So, current I will be equal to the potential difference V divided by R. And we are given the potential difference, or EMF, that is 230 volts, and the resistance is 25 ohms. The symbol we use for the ohms is omega. When I divide, our final answer for the current is 9.2 amperes. Part D. The current in the motor is 1.6 amperes. Determine the reading on the ammeter in Figure 7.1. Explain your answer. This is Figure 7.1. And we just calculated the amount of current. The current through the heater is 9.2 ampere. This is 9.2 amperes. And the current through the motor we just found is 1.6 amperes. So, the current through the ammeter would be the current coming from this branch, and from this, these two currents 9.2 and 1.6 will combine here, and it will pass through it. So, the total current through the ammeter will be equal to 1.6 plus 9.2. That gives us 10.8 amperes, and we will approximate it to 11 amperes. So this is an 11 ampere current that will pass through the ammeter, which is called the total current. So we can write our explanation that the total current through a circuit is always equal to the sum of all branch currents. The branch currents are 9.2 and 1.6. Battery is also providing 9.2 plus 1.6, that is almost 11 amperes of current through the circuit. Physics 0625, Paper 42, October-November 2024. Question number 8. A fisherman uses high-frequency sound to locate fish in the sea. Figure 8.1 shows the sound wave emitted from the boat. As you can see, the sound waves are approaching the seabed. Part A. State the name of the sound waves which have a frequency greater than 2000 Hz. Here, the prefix K represents the kilo, and kilo means 1000. Now we are very well aware that the sounds with frequencies between 20 Hz to 20,000 Hz are known as the audible frequency range. Frequencies below 20 Hz are called infrasonics. We name it infrasonics, and above 20,000 Hz are ultrasounds. Ultrasound, also known as sonography, has diverse applications in medicine, industry, and other fields. In medicine, it's used for imaging internal organs, guiding procedures, and monitoring fetal development during pregnancy. So here we would like to answer it as waves having frequencies greater than 20,000 Hz are ultrasounds. Question number 8. Part B. High-frequency sound wave travels from a boat through the seawater. The speed of the sound in water is 1,500 meters per second. The seabed is 22 meters below the boat. Calculate the time taken for the boat to receive the reflected wave from the seabed. After the sound is emitted, this is the situation. The sound waves are going towards the seabed, and then the echo moves back to the boat. So, moving towards the seabed, the sound waves cover a 22-meter distance, and after reflecting back, another 22 meter. So, the total distance traveled by the sound waves is 22 meters. Plus another 22 meters, which is 44 meters. We use letter V for the symbol of speed, letter S for the distance, and letter T for the time taken to cover that distance. By the definition of the speed, speed V is equal to distance S divided by time T. Here we are going to find the time taken, T, which is equal to the distance S divided by speed V. Now, substituting the values, the total distance is 44 meters divided by the speed, that is 1,500 meters per second. I got 0.0293 bar. 0.02933333 with the units, meter divided by meter per second. To find the unit of time taken, we can use method of keep, change, and flip. We are keeping m, changing the sign of division into multiplication, and flipping meters per second into seconds over meters. Meters cancel by meters. We get the second as a unit. So rounding the answer to two significant figures, we have 0.029 seconds as our required answer. Part C. Figure 8.2 shows a fish below the boat. This is the fish under the boat. Describe and explain how the reflected sound wave received by the boat from the fish differs from the reflected waves received from the seabed. We can see here that the fish is small in size as compared to the seabed. The size of the fish is this much, and the seabed is much larger than it. So the wave which will reflect from the fish will be having a very small wavelength. These waves will be weaker because the size of the fish is smaller. Secondly, this fish is near to the boat and seabed is farther apart. So reflected waves from fish, or the echo, will be heard sooner, as compared to the seabed. So, first of all, we will say that the fish echo will be heard sooner. Secondly, it would have been a weaker sound wave as compared to the echo from the seabed because seabed area is very large. So I can write this as an. It may also be weaker than the seabed echo due to the smaller reflection surface.
Question number 9. Figure 9.1 shows a wireless charging plate used to charge the battery in a mobile phone or a cell phone. The coil of wire is a part of an electric circuit. Wire is usually straight and coil of wire is like making rounds. It's world coil, a world wire. This is coil of wire. The charging plate is connected to an AC power supply. The power supply is turned on. Before I go for the question, I would like to talk about what AC is. We know that AC is alternating current that usually have an output like this. This output is in the form of sinusoidal waves. If this is the start of AC, this is called one cycle. In each cycle, half cycle is considered as positive, half cycle is considered as negative. Now, this positive and negative half cycle works like that current increases from zero, goes to maximum, and then becomes zero and changes its direction to the negative maximum and reaches to zero again. So this says that whenever the current starts as an AC, in every cycle it will change its direction with increasing current in one direction and decreasing to zero, and then it changes the direction from this. So if we say that its frequency is 450 hertz, so we can say in 1 second 450 times it will change its direction from positive to negative and negative to positive. Now coming back to the part A. The part A says describe the magnetic field around the charging plate in terms of magnitude and direction. The word magnitude means the amount, the size, the value. Magnetic field is always produced whenever we have a current carrying conductor. For example, if you have this wire, in this wire if current is going up, so there will be a magnetic field produced around it, and this magnetic field will have some properties. According to those properties, if current is upward, magnetic field will be anti-clockwise, and if current is downward, magnetic field will be you can say magnetic field will be anti-clockwise, and it will be dependent on the distance. If the distance from the wire is more, so magnetic field will be weaker. Similarly, if current is going downwards, so magnetic field produced around it will be clockwise in direction, and this clockwise direction uh, is shown by the Fleming's right hand rule, and it was told by Oersted first of all. If this current carrying wire is converted into a coil like this, if this is a coil, we usually name this coil as a solenoid. So what happened when current moves? So because of this current direction, magnetic field will be produced around it, and this magnetic field will be like this way, that it will have, according to right hand rule, the magnetic field direction, this will be north and this will be the south. And if we change, this magnetic field will change the north and south poles. And if it is changing from 0 to maximum, like in the case of AC, so what happened? The magnetic field strength also changes with the change of current, and it changes the polarity with the change of direction. So for example, for first half cycle, like from you can say O to A, what will happen? The current is increasing to maximum, so magnetic field also increase, and then current will from maximum to 0, magnetic field also you can say decrease from maximum to 0, but it will have in one direction. Let's say right side is north. But when current will change from A to B, what will happen during this portion of the cycle? The polarity will automatically will change. This will become north side and this will become south side, and it will also change the value of magnetic field. So this is we need to understand. So here we are asked that magnetic field around the charging plate in terms of magnitude. So it is understood that AC, the alternating current, as it is changing the value from 0 to maximum and maximum to 0, so magnitude of the magnetic field will be changing. When you talk about the direction, similarly, when magnitude of the current is changing and direction of the current is changing in every cycle, so it will have the different direction in each cycle. And also, the direction of the magnetic field will be perpendicular to the coil. Like I told you, that if this is the coil surface, so magnetic field direction you can see from both sides is perpendicular, so magnetic field is making 90-degree. And similarly, if this is the current, this is magnetic field in the form of single wire, so magnetic field and current are perpendicular to each other. So here I am going to write the answer. First thing, I am writing that magnetic field changes the direction and also the strength. Direction and magnitude both are changing because our power source is AC. The magnitude of the magnetic field is stronger near the coil. As we move away from the coil, it will be weaker, and also the direction of the magnetic field is always perpendicular to the coil. Question number 9, part B. A mobile phone is placed on a charging plate as shown in figure 9.2. We can see this is a charging plate and a mobile phone is placed on the charging plate. The coil in the mobile phone is part of a separate circuit that charges the battery. We can see the above one is the coil inside the mobile, and the lower one is the coil of the charging plate. The coil in the charging plate and the coil in the mobile phone act like a transformer. Before I go to the next part of the question, I would love to talk about the transformer first. A transformer is a device that we can use for the step up or step down the voltage. Here we have some primary voltage that produce a primary current in a coil which is called primary coil. When we have a primary coil, and for example this primary voltage is an AC voltage like this that keep on changing. So what happened is this input changing current produce, or you can say induce, a magnetic field. Because current is changing, this magnetic field is also changing. Let's say this one is the magnetic field produced due to the changing current. So this changing magnetic field will also induce current, and induced EMF will be observed here in the secondary coil. So this will be induced EMF and this will be induced current. Let's say this is induced current. So this secondary coil will show a secondary current that is induced, and this process is called electromagnetic induction. So this is called electromagnetic induction. What electromagnetic induction is? Electromagnetic induction is if the current changes in primary coil, due to which a magnetic field is produced in primary coil. This changing magnetic field induces a current and EMF in the secondary coil. And now, if number of turns are more or number of turns are less, so it will be step up or step down depending upon the number of turns in secondary coil. So, if you can say number of turns in primary coils are less, then number of turn in secondary coil, it will be step up, and if number of turn in primary coil are more than number of turn in secondary coil, it will be step down transformer. Getting back to the first part of the same question, explain why there is a current that I mentioned earlier on, induced current, in the secondary coil shown in figure 9.2. So as I discussed in detail, because of the electromagnetic induction, there is an induced current in secondary coil. So schematically, we will write it like as the AC input produces a changing magnetic field inside the primary coil, and this changing magnetic field induces EMF in the secondary coil, and this process is known as electromagnetic induction. Moving to part B, suggest why the transformer made from the charging plate and mobile phone as shown in the figure is not 100% efficient. First of all, there is not a real world transformer that will be 100% efficient. We just say an ideal transformer can be 100% efficient, an ideal transformer. So this is first thing we need to understand. Ideal transformer can be 100% efficient. First thing. Secondly, there are some issues here in this one. The first issue is there is some energy lost as a heat, maybe due to resistance of the coils, maybe due to eddy current. We know that eddy current, that is the backward current opposite to the actual current. Also, there might be another reason because this transformer does not have an iron core. When I draw this uh, transformer, so here in any transformer, in real life transformer, there is always an iron core. So for example, if I say that this is the primary coil, this is the secondary coil, both of these coils are uh, what you call are whirled over an iron core. So this iron core help to induce more current and EMF in the secondary coil. So I would prefer to write the answer. Energy is lost due to heat and resistance in the form of thermal energy, and also I told you eddy current. There is no iron core present like a transformer, actual transformer. That's why it cannot be 100% efficient. And I also told you that real world transformer can never be 100% efficient. Only the ideal transformer can be. Question number 9, part C. The mobile phone battery can be recharged using the charging plates and stores 4.5 times 10 to the power 4 joule energy. Usually we represent energy by E. When fully recharged, the current that we usually represent with symbol I in the secondary coil is 0.63 ampere. The output voltage is 12 volt and voltage we also represent by the V. Calculate the time taken to fully recharge the uncharged battery. Time taken is represented by T. This is our unknown. So electric energy is usually E is equal to I V times T. This equation is taken from energy is power delivered into time. So here we need for the time, what we will do, we can just rearrange this IV on the other side. So the time will be energy over I times V. I am using this equation. When I will use this equation, so I can simply say time is equal to 4.5 times 10 to the power 4 joule over 0.63 amperes current times 12 volt. When we use the proper units, joule, ampere for the current and voltage for the potential difference, the time will be automatically measured in seconds. So I'm just solving it. 4.5 times 10 to the power 4 divided by 0.63 times 12. What I got is 5952.4 seconds. So I can just simply say 6000 second, but I will prefer to write in scientific standard form, scientific notation. So I will write 6.0 times 10 to the power 3 seconds. The second part of the same question is calculate the charge passing through the battery in 60 seconds. Here, I would like to remind you charge is denoted by Q, that is unknown for us, and the time represented by T, it is 60 seconds. To solve this problem, I will use the definition of the current. Current I is known as rate of flow of charge, means charge passing through a point per second. So I can say I is equal to Q over T. Here Q, the charge is unknown, so T, which is denominator, will move on the other side. So the equation will change. Q is equal to current I times time T. By substituting the values, Q is equal to 0.63 amperes times 60 seconds. I got 37.8. So charge is 37.8 coulomb, that is rounded to 38 coulombs. Question number 10. Carbon 14, 6C14, is a radioactive isotope of carbon. Carbon 12, 6C12, is not radioactive. Before I go to solve part A, I would like to talk about two things. First of all, any element can be represented can be represented by a symbol X. Here we write Z, here we write A. Here Z is representing atomic mass number, atomic number, whereas A represents mass number or number of nucleons. You can say number of nucleons. What does it mean? It means that atomic number contains only either number of protons in that atom or number of electrons revolving around the nucleus, because number of protons are equal to number of electrons. So we can simply say the number of proton are equal to make an atom neutral. So this is it. When we talk about mass number A or number of nucleons, it means that number of proton inside the nucleus plus number of neutrons inside the nucleus. So total number of nucleons is represented by this. So here we are talking about two carbon isotopes. One is 6C14 and other is carbon 12. What are these two isotopes for? First of all, an isotope is an atom, is an element with the same number of isotope have same number of proton or electron, or you can say same atomic number atomic number, but different mass number, different mass number. So we can say they will be differing only in the number of neutrons. So you can say number of neutrons are different. These are two isotopes of the carbon. This is carbon 14 and this is carbon 12. Here I would like to mention that it has atomic number A, 6 for carbon 14 and 6 for carbon 12. It means that it has 6 protons and 6 electrons, and carbon 12 also has 6 protons and 6 electrons, but mass number is 14 for carbon 14 and 12 for carbon 12. It means that being 6 proton, it will have 8 neutrons, and it will have carbon 12 will have 6 neutrons. So they are different in this case. And secondly, there is another thing. We said that carbon 14 is radioactive. Radioactive mean it can spontaneously start emitting the radiations like alpha, beta, and gamma, and it will start decaying, and it will have a half lifetime within which it will change the total amount into half. And also the carbon 12 is non radioactive, that it is not going to decay. So these are the two words also used in the question. Now getting back to the question part A, explain how an atom of carbon 14, 6C14, differs from an atom of carbon 12. So, as I mentioned in my explanation, that carbon 14 contains equal number of proton, electron, or atomic number is equal, mass number is different than the carbon 12. It has 8 number of neutrons and 6 are for carbon 12. So I would like to write this answer in this way, that carbon 14 contains 8 neutrons, sorry, whereas carbon 12 has 6. So carbon 12 has two neutrons lesser than carbon 14. So we can also say, in another word, that carbon 14 is heavier than the carbon 12. And also, I can mention here, carbon 14 is unstable isotope because it is mentioned that it is radioactive isotope. It will start emission of radiation at any time, whereas carbon 12 is not radioactive, it is a stable isotope of the carbon. Part B. All living organisms contain carbon 12 and carbon 14 atoms. The ratio of carbon 14 to the carbon 12 is this. This one is mentioning carbon 14, and 1 into 10 to the power 12 is carbon 12. Carbon 14 has a half life of 5,700 years. I would like to repeat one more time that any element, any isotope of an element that is unstable, or we can say is radioactive, it can start emission of radiation anytime. When it starts emission of radiation, its amount start decreasing. So the time within which half of the atom decays, that emits the radiations, and half left, we call it half lifetime. So carbon 14 being unstable, carbon 14 being radioactive, decays, and after decaying it takes 5,700 years to become half of the original amount. For example, if original amount of carbon 14, let's say, is 1 kilogram, so after 5,700 years it will go to half kilogram left, and after another 5,700 years, that will be 10,400 years, sorry, 11,400 years, it will change into half of this remaining, that is 0.25 kilogram. So we can say after first half life, the radioactive isotope changes into one half. After another second half life, it changes it to one quarter, and so on, so forth. So now we can simply say that we can simply solve it like this, that when an organism, part 1, when an organism dies, no new carbon is absorbed, that we are not going to have more carbon absorbed. The amount of carbon 12 in the dead organism is fixed because it's non-radioactive. So describe how the amount of carbon 14 in the dead organism decreases. As we know that it's a radioactive, it is unstable, so it will start decaying. It will emit the radiation. Due to emission of radiation, after 5,700 years, it will remain the half. After 11,400, it will become one quarter, and so on. So I would like to write here, after every 5,700 years, the amount of carbon 14 reduces to one half of its original because it is a radioactive. Secondly, as time passes, each half life reduces the remaining amount to half. That in first half life, if it was, for example, 100%, it will be after first half life become 50%, and that 50% after second half life will change into half, 25%. After another half lifetime, it will change into 12.5% and so on. Question number 10b, part 2. A sample of wood contains carbon 14 to carbon 12 ratio as 1 ratio 4 times 10 to the power 12. Calculate how many years ago the tree died. We know that the ratio of the carbon 12 is always fixed, it is not decreased, whereas carbon 14 decreases with the time. So carbon 14 is showing the decay process. And half life for carbon 14 is given in previous part 5000 second 700 years. Now the ratio we are given here is carbon 14 ratio carbon 12. It's 1 ratio 4 times 10 to the power 12. It shows that after first half life, first half life, it changes to 1 ratio 2 times 10 to the power 12, and after second half life, it changes to 1 into 10 to the power 12 years. That was mentioned in all living organism. Usually the ratio of carbon 14 to carbon 12 is this. It means to move from this fixed ratio of living organism to 1 ratio 10 to the power 4 times 10 to the power 12 is having two half lives. So two half lives means, so time taken is two half lives times half lifetime. Half life time. Total time taken is 2 times 5700 years. That goes to 11,400 years, and I will round it to 11,000 years. There is one more thing that I need to mention for this two half lives explanation. What is that one? That, for example, you say that the ratio of 1 into 4 times 10 to the power 12 mean after first half life carbon 14 change into 50%, decreasing 50%, that will change into zero point 0.5 times 1 into 10 to the power 12, and another second half life it will decrease to 25%, that is 0.25 ratio 1 into 10 to the power. So if I want to make the ratio in digit form, so I will multiply by 4, 1 ratio 4 into 10 to the power 12. That is the given after two half lives. Part C. Other radioactive isotopes have different half lives. every isotope has different half-lives. Some are having short half-lives, some have very, very long, like we see in carbon 14, it's 5,700 years, and some have uh, very short in minutes or seconds. Suggest a use of radioactive isotope with a half-life of 1 hour. So this is having a short half-life time, short time. So when any radioactive isotope having a short half-life time, so it can be quickly uh, decaying, and quickly its effect can be reduced. Its effect can be for the short interval of time, so it will be less harmful, or sometimes we can say it's almost harmless, because it will stay on the object for less time, so these radiation can finish quickly because the atom is having less half-life time. Explain why a short life is suitable for this. So we are having any radioactive isotope which is short half-life time. So the use of this can be as a medical tracer, or medical images, or imaging, or medical diagnosis. As I told you, why it is useful, because short half-life time, exposure, and limits the exposure. It is for very short time and causes it to decay quickly, and it can be less harmful. So here we can also add up that it is for short time, so you can say it is less harmful, and it will be for lesser time affecting the object.
Physics 0625, Paper 42, October November 2024. Question number 11. Part A. State the name of one planet that has an orbit further away from the Sun than Venus. Let me remind you about our solar system by using this diagram. We know that our solar system consists of the Sun with 8 planets orbiting around. The planet that is closest to the Sun is Mercury. Considering the order of increasing distance, next Venus, Earth, Mars, and up to Neptune. According to the question statement, which planet is further away from the Sun than Venus? Venus is the second planet that orbits around the most closer to the Sun. Further than Venus are Earth, Mars, Jupiter, and so on. We can write any one of these here. When it is closer to the Sun than Venus, then it's only Mercury. And first, we have to name the planet that orbits further away from the Sun than Venus. We can choose either the Earth, Mars, Jupiter, Saturn, Uranus, or Neptune. Second part requires the name of one planet that has an orbit closer to the Sun than Venus. The only planet we should mention here. It's Mercury. Question number 11. Part B. Venus has an average radius of orbit 1.1 by 10 to the power 11 meters and an orbital speed of 220 Earth days. Calculate the average orbital speed of Venus. You must write your answer in meters per second. We know that the orbital speed of a planet is denoted by v, which is equal to 2 pi times r. Letter r represents here average radius of the orbit divided by t, and letter t represents the period. Here, I would like to mention that the speed is measured in meters per second, which is required in the question. We measure the radius in meters. and the period is measured in seconds. Here I would like to remind you that one day is equal to 24 hours, each hour is 60 minutes, and each minute is equal to 60 seconds. To convert from days to seconds, we will use these relations. So what I'll do? I'll rewrite the equation here and substitute the values in the equation. V, the orbital speed, is equal to 2 pi times r, the average radius, which is equal to 1.1 into 10 raised to the power 11 meters, divided by t, the time, which is 220 Earth days. "24 hours into 60 by 60. Hence, it is converted into seconds. V, the orbital speed becomes 36,361 meters per second. In scientific notation, we can simply say 3.6. As decimal move from here till here, so it moves 4 digits. I'll write 3.6 into 10 to the power 4 meters per second. The required result for the average orbital speed is 3.6 into 10 raised to the power of 4 meters per second. Question 11. Part C. State the relationship between the orbital speed of the planet and their distances from the Sun. To understand this one, we need to review Kepler's second law, in which he tried to tell us that the orbital speed v is inversely proportional to r, the average distance of the planet from the Sun. If the speed is higher, the average distance, r, of the planet from the Sun is less, which means the planet is now very close to the Sun. Kepler, in his first law, mentioned that the orbit of a planet is not circular but an oval-shaped one. Let the Sun is situated here. When the planet comes closer to it, will move faster, and when the planet is farther apart, it will move slower. More the distance, the slower the speed. The variation in speed is due to the gravitational pull of the Sun. As a planet gets closer, the average distance reduces, and the gravitational pull of the Sun increases. Hence, the planet moves faster. We can also say that the further away from the Sun, the slower is the orbital speed of a planet. Or, closer planets orbit faster due to stronger gravitational pull. In this simulation, it's the elliptical-shaped orbit. This is the Sun. And this dot represents the planet's positions. This is the farthest point, and this one is the nearest point. We can see that at the furthest point, the planet's speed is 17.24 kilometers per second. As it starts moving toward the near point, its speed is increasing, and it's the maximum here at this point, and then it starts slowing down. This is a clear picture of how Kepler tries to explain the distance and speed relationship. This variation in speed is due to the gravitational pull. The last part of question 11 is D. Comets are balls of ice and dust. Some comets orbit the Sun. State how the speed of the comets changes as it orbits the Sun. Explain your answer using the ideas about the conservation of energy. You may include a labeled diagram. Let me start with the diagram. First of all, we need to remember that if this is a sun, comets orbit the sun in an elliptical path. When a comet is at this point, which we name as a near point, and this one is known as a far point of a comet. The Sun is situated at the focus of the ellipse. This is comet's near point. And the other one is far point. What happens to the comet's speed when it is at the near point? Here, it will have more speed and more kinetic energy. But lesser potential energy and small amount of average distance from the Sun. Keep it in mind that total energy is conserved, which will remain the same throughout the orbit. When it is at a far point, speed and kinetic energy are less. Whereas average distance of the comet from the Sun is large, potential energy is also large. But again, total energy will be same because of the conservation of the energy. So we have to remember that this orbit is elliptical, or you can say oval in shape. It cannot be round like a circle. So I would like to mention that the orbit of the comet around the Sun is elliptical. We conclude that the speed of the comet is faster when it is at its nearest point, or closer to the Sun. Or the speed of the comet is slower when it is further from the Sun. It will contain more kinetic energy and less potential energy when it is near the Sun, but it contains more potential energy and less kinetic energy when it is further. But according to law of conservation of energy, total energy throughout the orbit will be the same. Thank you so much. I hope you understood well. Keep watching my videos on the physics pages and don't forget to subscribe and share.